Hello again. This is Unit 6 where we don't technically learn any new stuff, but we start chaining together skills that we picked up in the other parts of Unit 0. So let's see what that means. They say, sodium reacts with chlorine to produce table salt, sodium chloride. So they tell us our reaction is sodium reacts with chlorine, which is diatomic. And from that we get sodium chloride. It's a formation reaction. And let's balance that because we normally do. Two chlorines on the left means we need a 2 here, but now we have 2 sodium on the right, so we need a 2 here. And we'll put a 1 there just to fill things out. So we know that as far as moles, this thing has a 2 to 1 to 2 ratio. And now they're saying we want to end up with 100 grams of sodium chloride. The mass of sodium chloride is 100 grams. Now, these ratios only work with moles, so we can't say there's 100 grams of this, so there must be 50 of chlorine and 100 of sodium. It doesn't work like that. But we can get a number of moles from this. We know that the number of moles of anything is its mass divided by its molar mass. For sodium chloride, that would be the mass is 100 grams. The molar mass is, oops, don't have it. Quick side trip. NaCl is made of sodium with a mass of 2299 and a chlorine, which is 3545. 14 carry a 1, 14 carry a 1. 3 plus 5 is 8, and 2 plus 3 is 5. So 5844 is our molar mass. And 100 divided by 5844 tells us we have 1.71, let's carry a little extra, moles of sodium chloride. So if we have this number, we know the moles of sodium chloride. The chlorine moles would be half that much, 0.85 or so, and the sodium moles would be the same. Because this is a 2 to 2 ratio, those numbers are equal. That means we must also have 1.711 moles of sodium. They just said how much sodium is required, so technically we could stop here, but let's get a mass also because they could easily have asked for the mass. The mass of sodium is number of moles of sodium times its molar mass. 1.711 moles of sodium, and the molar mass for this is 22.99. Each mole of sodium has a mass of 22.99. Multiply those together and we get 39.3. 39.3 grams of sodium metal would be needed to start this reaction. So because they just said how much sodium is required, technically either of these would be an acceptable answer, but definitely know how to get the mass also, because quite often when we ask these questions, we wouldn't just say how much sodium, we'd say how much sodium in grams or what mass of sodium is required to make blah, blah, blah. Fair enough. So it's get moles, jump to another substance, and then maybe use those moles to find a volume or a mass or whatever other quantity they ask for. Calcium reacts with iron 3 oxide to produce iron metal and CaO. All right. Bit of an unusual reaction, but they spelled it all out for us, so it's probably going to be okay. Calcium, the metal, reacts with iron 3 oxide. I trust you're pretty confident with these right now, so I'm just going to write Fe2O3. Plus 6 charge from the irons, minus 6 charge from the oxygens. And that produces iron metal, which is plain old Fe, and calcium oxide. Can we balance this? Um, 3 oxygens means I need a 3 here. 3 calciums means I need a 3 here. And 2 irons means I need a 2 here. Okay, that wasn't so bad. And we'll put in a 1 there just to fill the space. So 3 to 1 to 2 to 3 is our ratio. They want to know how much iron is produced if we're starting with 80 milliliters of iron oxide solution at a concentration of 0.423. So all our information at first is about the iron oxide. They tell us its volume, which is, I'm not going to write 80, why not? They gave us milliliters, which is a unit we do not like. 80 milliliters is 0.080 liters. This concentration is in moles per liter. Because of that, we're kind of stuck using liters for our volumes. So anytime you see mils, just convert them instantly is my advice. Saves trouble. Concentration, they said, is 0.423 moles per liter. And if you know the concentration and volume of something, you can do N equals CV and get a number of moles, which we definitely want. If you can't get moles of anything in chemistry, you are in trouble. 0.08 times 0.423 gives 0.03384. 0.03384 moles of iron oxide. So the moles of calcium will be 3 times this much. The moles of iron will be 2 times this much, and the moles of calcium oxide will be 3 times this much, and they want the iron, this. So 1 to 2 ratio tells us the moles of iron will be twice as much as the moles of iron oxide. So take this number and double it, and we get 0.06768 moles of iron metal. Now, again, they just said how much iron, and by they I mean me. I wrote this question, so I was a little bit lax with my phrasing here. You're technically okay to stop here and just say how much iron? 0.06768 moles of iron. Let's also get a mass, though, because it's good to know how to do that. The mass of anything is how many moles of it times what is its molar mass. 0.06768 moles times the molar mass of iron is 5585. And that gives us a mass of, I thought I saw 37, 3.78. 3.78 grams of iron metal. So that answer is good, or because the question left it kind of open what units they wanted, giving the number of moles would also be okay. All right. Sulfurous acid neutralizes potassium hydroxide. All right, so we have an acid and a base fighting in this reaction. Sulfurous acid, H2SO3, they say neutralizes, which is short for reacts with potassium hydroxide. Potassium's +1, hydroxide's -1, and that produces potassium sulfite, K2SO3. I'm kind of gliding over the producing the compounds because you've had a ton of practice. I hope that's okay. If it isn't, your instructor is right there. They will be happy to go over this with you. And HOH. It's good when you're doing acid-base reactions to write your water as HOH, and what you do then, let me just do some color coding here. This hydrogen in the acid we consider to be the same thing as this hydrogen here. They're both the positive ions. And this hydroxide we consider to be the same as this hydroxide. So that's a little weird. We're counting hydrogens 2 different ways, but this really does work and it makes them easier to balance, I think you'll find. So when we go to balance this, we'd say we have 2 hydrogens which means we needed 2 here, 2 of the orange hydrogen ions. Now that means we have 2 hydroxides, which means we need to double our KOH. That means we have 2 Ks, which is all right. And here we have 1 sulfite and 1 sulfite. So now we're all balanced. And we'll put 1s in those spots to make it all nice. And they tell us we have 120 milliliters of sulfurous acid, instantly converted to liters. And that reacts with 75 milliliters of potassium hydroxide, instantly converted to liters. And the concentration of the KOH was 0.585 moles per liter. So this is the volume, this is the concentration. Sorry, that's a little bit off the edge, I can tell. Okay, so in general, start where you can get the number of moles of something. We don't know enough to do that for the sulfurous acid, but we do know it here. We have a concentration and a volume there, so we can say for the KOH, our number of moles equals concentration times volume. So it's 0.585 times 0.075. 0.075. And we get 0.043875 moles of potassium hydroxide. Now they want to know about the sulfurous acid, and because the ratio here is 2 to 1, we know our sulfurous acid is always going to be exactly half as much as the KOH. It's 1 out of 2 as much. So if you multiply this by 1/2 or divide this number by 2, you'll get the number of moles for the H2SO3. It's this number divided by 2, and that gives us 0.021937.5. And that's moles. Now what they were asking for here was the concentration of the sulfurous acid, and we have enough to find that now. We have our formula that we usually use as N equals CV. If you want to find concentration from that, we can manipulate this formula. If we want C by itself, just divide both sides by V, by volume. Those volumes cancel out, and we get the concentration of something is how many moles of it divided by what volume is it dissolved in. For the H2SO3, that's 0.021937.5 moles divided by, it's in a volume of 0.120 liters. And when you divide that out, you get a concentration of 0.1828. What do we have for digits here? I guess technically this should only have 2 digits in the answer, 0.18. And its concentration, so the units are moles per liter. There's a separate lesson where I go over significant digits if you're curious why I trimmed that down to 2 digits. But if you got 1828125 on your calculator, then you're doing the right thing. So that's our concentration for sulfurous acid. So again, get the moles of the first substance, the one that we start you off with. Use these ratios to jump over to moles of your second substance. That's where we took these moles divided by 2. And then you can use those moles to find whatever else you need. And you've noticed we haven't been practicing the gas stoichiometry very hard because there just isn't a lot of it in Chem 30, but here's one question. And it's about hydrochloric acid with zinc. So HCl is hydrogen chloride or hydrochloric acid, and it reacts with zinc metal. We get zinc chloride, and we get hydrogen. So this is a single replacement reaction. And when we balance it, 2 chlorines means we need a 2 here. 2 hydrogens is actually okay, and we have 1 zinc on each side, so not too complicated on the coefficients. And they tell us we have 3 grams of zinc. Just from that, we can get a number of moles. The number of moles for zinc is its mass divided by its molar mass, which means it's 3 grams divided by the molar mass of zinc, which is 6541. Just zinc metal. So 3 divided by 65.41 gives us 0.045865 moles of zinc. They're asking about the hydrogen, and oh, how nice. It's a 1-to-1 ratio. So however many moles of zinc we will have exactly the same amount of hydrogen. Our number of moles here is, again, 0.045865. Now they're asking for a volume, and because we're talking about a gas, the formula that covers this is the ideal gas law. I believe on our formula sheet it's written PV equals nRT. In this unit we've been using it a lot as N equals PV over RT. Neither of these is fantastic for what we're trying to do now. We want to get a volume V. So if you take this version, which is probably the best to start with, if you want to isolate V, we're just trying to find a volume, then we want to divide both sides by the pressure. On the left side, the pressures cancel out. Ignore that. And we get volume for an ideal gas is nRT divided by P. Now, forgive me, I'm hurting a little for space, so I'm going to move this over into the blank on the left. That means the volume for the hydrogen will be its number of moles, 0.045865, times the ideal gas constant, 8.314, times its temperature. Did you think about writing 25? I hope not. This is a Celsius temperature, and remember, temperatures for the ideal gas law have to be in Kelvin. For Kelvin, we're looking at 298.15. Sorry, pink writing, you gotta go, we need the room. 298.15 Kelvin, and our pressure is 100 kilopascals. So multiply by 8.314, multiply by 298.15, divide by exactly 100, and we get that our volume is 1.14 liters. And that's how you do that. So again, they gave us enough information to find moles of zinc. From moles of zinc, you can jump to moles of anything else. In this case, we needed hydrogen. And once you get the number of moles of hydrogen, then you can finish the problem up. That's the general pattern when you're doing stoichiometry. And just as a quick peek of what's ahead, this is not really part of Unit 0, but just in case you were wondering, in Unit 1, we're going to write reactions that are things like, often it'll be what happens when you light something on fire. So we'll have a reaction, and in addition to all the chemical species that are in there, we'll teach you to work in the amount of energy that this produces. So you'll take this reaction and you'll balance it. And in addition to all the chemical species, you'll find that maybe, I don't remember what the real number is, but we'll tell you how to find how much energy is released when you complete a chemical reaction. And so You might find I've got this many moles of propane, therefore this much heat will be released when I burn it. In a lot of ways, heat behaves just like another chemical, and you can use mole ratios to figure out 1 mole of propane will give me 5 moles of oxygen, or will use 5 moles of oxygen, produce 3 moles of carbon dioxide, and give me this much heat. So we'll do energy calculations like that. In Unit 2, something similar to this will happen where we'll look at what if you have a reaction where you're transferring electrons between a couple of species. For instance, you might have copper ions and you're going to put electrons into them and turn them into copper metal. You can count the moles of electrons just like anything else. So you could say, if I want to make this many moles of copper, how many electrons will that cost me? And we'll also show you how to convert from electrons to electrical energy. How many amperes of current or how much voltage for how long must I generate in order to make this copper? So in Unit 1, we use these ratios and we work in heat. In Unit 2, we use these same ratios and we work in electrical energy. Unit 3, honestly, doesn't use this stuff very much. It's organic chemistry, it's a very different animal, and you'll get a bit of a break there. And in Unit 4, we're back to doing this where we're looking at acids and bases. So in that unit, you'll have things like we start out with an acid, and it reacts with water and gives away some hydrogen. And we'll be interested in how much released hydrogen there was because the strength or the effectiveness of an acid or a base depends on its ability to either give away hydrogen or take away hydrogen from others. So in this case, we'll be working out how many moles of acid did I have. From that, how many moles of hydrogen am I going to get? And that'll tell us about the pH of solutions and what effect acids and bases have on each other's pH when we mix them together. So I hope you have a feeling already that this has been worthwhile practice, and definitely you're going to see it in 3/4 of the upcoming course. I'll see you soon as you get into those units. I hope that all goes well for you. And as usual, if you have any questions or concerns about it, the instructor's never far away. Don't hesitate to get in contact with them if you want to talk about any of this. The teachers in this course generally are chemistry geeks, so they'd enjoy going over it with you. Best wishes. We'll see you soon.